Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is chapter 6, section 6.1. Okay, so we start off with this subsection 6.1.1 entitled The Quest for Freedom. So what we're going to be working with here is we're going to be working with three modules, meaning we're going to be working with things that have maps between them that can be represented by matrices. Okay, and a matrix is enough to describe the map. So we need to discuss what we mean here, what kind of modules we'll be working with. We're going to be working with ones that are over a field. What's a field? It's a ring where the only thing that doesn't have a multiplicative inverse is 0. So for instance, Z mod a prime, or the rational numbers, or the real numbers, the complex numbers. And so if we think about modules which have outside scalar multiplication by a field, that all of a sudden is a vector space. Vector space is just the name for that. They come from the idea of vectors and working with them, tuples of things. And there's different vector operations. You can add vectors together. That's like the group thing, but also you can have outside multiplication. You have a scalar multiplication outside, which makes it into, when you're dealing with vectors, and it makes it into what we call a vector space. Or you could say, if you're working over R, okay, over the real numbers, then oftentimes we have an R module. An R module is a vector space, for instance. So anytime you're dealing with vectors, you're actually working with modules. Module is just a more generic term. If the module is over a field, meaning that the scalars or the outside multiplication is by field elements, then it's all of a sudden called a vector space. Okay, so what is a vector? At least in our terminology for now, let's start with this. So a vector is just going to be a tuple of things. So we're going to be looking at like if our free R module is over R, for instance, then okay, let's just get this out here. Then we have so like then what we're going to do is our modules are going to be of this form. Our vector spaces, they're going to be like this, something like this, and we can abbreviate the notation like this. And elements of this are just simply tuples of things that are in the real numbers. So we're going to call the elements of modules that look something like this. So if the scalar multiplication is by real numbers, we're just going to call that a vector. Okay, so the elements we're going to call vectors. That has a lot to do with its interpretation. If we're thinking of a vector as being an arrow with a length and a direction. For instance, so if we're in 3 space, there are 3 dimensions, this 2, 3, 4 could represent a coordinate point representing the tip, and the tail is at the origin. And so you can quite literally think of each tuple as a vector. They add the same way as vectors would with arrow addition, if you're familiar with that. But simply you're just adding component wise, because you add in each, because each component is like its own group, additive group, and you're adding in each one. It's the same idea. Okay, so okay, going from there, what we want to be able to do is we want to be able to study merges of vector spaces that preserve the vector space structure. All right, and that often can give us some new insights into what we're studying, what we're working with. Sometimes we represent different vector spaces in in kind of different ways, and they mean different things. And if we can view them in after a merge that's preserved structure, then we can see new things we didn't see before. In the same way that we could do that with Boolean algebra, when we were taking finding merges that preserve structure, we could, looking at the different fibers and so forth, we were able to actually pump out sandwich swallowing, even to be able to, earlier in this book, at least the technique that I labeled as sandwich swallowing, in order to optimize Boolean algebraic expressions. Same type of way. It gives us more insight. It allows us to see things in a new way. So we're going to be talking about merges of vector spaces. So like R3 we'll consider as a vector space. It's it has an outside multiplication by R. So or scalar multiplication. So and things that have a nice scalar multiplication that kind of has the properties of outside multiplication on the ring, outside multiplication on the additive group of three tuples, then we're good to go. Then we have a vector space. Okay, so since it preserves vector space operations, in particular, it preserves the additive group structure. So not just the outside multiplication, but it preserves the additive group structure. So we basically have a merge of a group. Now, merges of groups that preserve the operation, end up being, so it chunks into things that are just called cosets, and cosets of a subgroup. In fact, wherever the zero element, like this additive identity, goes in the merge, like that whole chunk that it's in is actually always a subgroup of the original, and all the other fibers of the merge or the of the surjective map, or all the other chunks are actually just shifts of that or cosets of that. So kind of we can be using that idea as we go along, just kind of remembering that. Let's see, outside multiplication is actually a map that preserves addition. It must preserve the added identity. It's additive identity. So k times 0, 0 is that. All right. Oh, okay. So we notice here that if we have, so this merge, even if we just merge, okay, in here, preserves the R module structure. Okay, so if we want, if we want the R module structure to be reserved by the merge, we also need this idea to hold. So k times, so outside multiplication times anything in here has to also be in here again. So that basically means that outside multiplication is closed on this subset, meaning that this subgroup is more than just a subgroup. It's actually a subvector space, which often we call it as a subspace. So it's a subset of R3 that actually ends up being a vector space itself, in and of itself. Okay, so great. All right. So wherever 0 lands is not just a subgroup, it's actually a subspace. It's actually a vector space in and of itself. Okay. In fact, we actually get the fact that the quotient, by modding out by this, actually ends up being a vector space, and this ends up being a vector space too. And both of them kind of are in some way isomorphic to something like R3. Maybe it's like isomorphic to R or R2 or whatever. It's kind of neat working with vector spaces because subspaces, as well as quotients and merging and everything, they all end up being free, and they all end up being in a sense that they're like just tuples of things. So free, loosely for now, you can just think that free means somehow isomorphically, which means they have the same structure as, you might have to relabel a little bit, has the same structure as something that has tuples. Okay. So all right. Okay. And in here, actually, there's a discussion. This discussion talks about deciding how how these guys are actually free as well, and can isomorphically have kind of a tuple structure in how they work. So in particular, let's see, if we merge, okay, so with the red bar, we get a new vector space. And in this vector space, we'll notice that certain things, for instance, okay, let's see, look at this particular example here. Okay, all right, suppose that we would like 1, 3, 2 to merge to 0. All right, so if that happens, then what's going on? So if 1, 3, 2 merges to 0, then okay, all right, so then this is going to be the smallest vector space that contains both 0, 0, and 1, 3, 2. All right, we'll just notate it this way, my 1, 3, 2. All right. Okay, if we also assume minimally that 1, 1, 2 must be in there, then we would call this the span of this. Okay, so the smallest vector space that contains those two vectors basically sums of scalar multiples of these. So scalar multiples meaning you just apply an outside multiplication this, outside multiplication that, you kind of add them together. And it kind of fills out to be a vector space in it, a sub-vector space in and of itself. And that one is actually going to be this one right here. Okay, that's going to be what the additive identity in the R3 is going to become when we at least what it's going to the chunk that contains it is going to be that vector space in the merge. Okay, so, and compact set builder notation, actually, this is how we could represent what the span of that looks like. Basically, just taking R multiples of this plus R multiples of that and just kind of filling it out. Okay. All right. So, all right. So in this case, all right, something like this. So just if you take all R multiples of a vector, then basically I give you an R multiple, a value of R, and you can tell me, you could just apply it to this and you get a vector out, meaning that the actual elements of R are in 1-1 correspondence with the elements of the span, meaning that it's kind of like through a relabeling process. If you kind of like relabel this as like as 1 even, if you like, you actually get an isomorphism. This is actually isomorphic to R. So like, so you could say a degree of freedom of 1. Degree of freedom, loosely for us right now, just intuitively, we could think of that as simply being rank, dimension, however you wish to think about it here, R1. Okay, so this little 1 right here, isomorphically, this vector space right here looks like R1. All right, and this one right here, actually, isomorphically can actually be rewritten as R2. All right. Except it's kind of interesting because if you look at this, actually the span of this vector is actually equal to the span of this vector as well, or is the span of these two vectors. But notice that this vector is actually a tag along. It's actually already in the vector space span by just 1, 3, 2, because you just double this, you get that one. So really this one was unnecessary. So there's kind of like a minimal set of vectors that span. And once you find that minimal set of vectors that span and you count how many you have, that actually will give you that number. So to get that degree of freedom right there. I mean, this is a little intuitive right now, but that's kind of the basic idea with that. And that concludes this first little read along of section 6.1. Thank you for watching.